You have a lot to talk about. And it's good to see you back after the coffee break. Normally we have some more empty chairs after the coffee break, but it's, well, I think 2 or 3 empty chairs. Good to see you back. Normally we say in Dutch, I will say it in Dutch, hè? Kennissen is goed. Nee, kennis is goed, maar kennissen is nog beter. If I translate it, knowledge is good, but to have good acquaintances is even better. So the coffee break, I think, and the lunch is the best part of the Congress these days, because then you can meet and you can talk about our profession, and that's good. Our second speaker of today, Robin Zevotek. I pronounce it? Okay. Robin began his career as a firefighter, and in 2002 he started studying firefighting tactics. Robin worked in the world of operational firefighting for 10 years, and he still is, and he worked in the world of research. At the moment he is working at the UL, Underwriters Laboratory, as a research engineer working in the Firefighter Safety Research Institute. His specialties, that's a bit difficult, fire protection alarm system design, special hazard system design and building information, modeling and integrated design. That needs a bit of what it is. May I have your attention for Robin Zevotek, what we've learned from 10 years of research with the fire service.
Thank you. Thank you. Good morning. Thanks everyone for coming back from the coffee break. Since that's the most important part, we could just take another coffee break and everybody be happy, right? That'd be okay. Thank you very much for the opportunity again to come and share our work with UL for both the fire prevention and operations side of the fire department. They are both equally as important, and as they work together, they provide us with an opportunity to take knowledge and pair it with experience. And when we do that, I feel we get the best of both worlds and can use them together. So my presentation today is looking a lot at knowledge, but we're trying to pair that knowledge with specific experience-based tactics on the fire ground and how we can use those in operations. My background started as a fire safety engineer. We call them fire protection engineers in the United States. So I started designing fire alarm systems, fire suppression systems. At the same time, I was working as a firefighter, or we volunteer as firefighters there, and volunteers are very different in the US. There's no compensation associated with it. So if you ask my wife, it just costs me money to volunteer, which she's probably right. It costs a lot of time as well, but at the same time, I was able to kind of pair the best of both worlds as I started at UL in 2014 and started working towards firefighter research specifically. So where do I work? Well, I work in a group that tries to hit the message of UL at the same time helping the fire service. So UL's goal as a global company is to promote safer living and working environments. And in the fire service, we have the opportunity to hit 2 of those at the same time. Often, your living environment is where the firefighter is going to work. When there is a fire or an incident, that's where they show up to. So if we can make your living environment safer, we inherently make their work environment safer. And if we can make their work environment safer, we make your living environment safer at the same time. So we're dedicated to more increasing of knowledge. Not necessarily how you do something, but why it is done and what you can use to support that. As an engineer, if you write a report, you have to cite information. I cannot say that 2 + 2 = 4 in an engineering report without first, little simplistic, but referencing where that came from. I can't say that the amount of toxic gases you need before you reach a fatal dose is this without referencing somewhere where that information came from. In the fire service in the US, that's not the case. If I were to grow a really nice mustache, I would have spent a lot of time in the fire department. Whatever I said was right because I did it so often. It's a little joking, but there's a little bit of seriousness associated with the experience. So how do we pair both of them together? to be able to come up with essentially the best we can be as operational firefighters. So how do we do that? Typically, especially in the US, the top chain there is our formal way of developing guidelines for operations on the fire ground. We have a book. When you join the fire department as a volunteer or you're appointed as a professional firefighter in our country, they give you some book. That book varies very much so across the country based on different organizations, different types of tactics. You memorize the book, you train on the book, you apply the book on incidents, hopefully correctly. You critique how that went, and then hopefully revise what happened back into your strategies and tactics. The challenge with that is that we don't have as many fires as we used to. In the 70s in our country, they say that firefighters were going to a fire every shift that they were on duty. In some areas, they were going to 5 every 12 or 24 hours that they were on duty. Now they're lucky to go to 1 every time they're on duty. And in some instances, they go months between incidents. So if that's the case, how can you critique something that happened this month compared to something that happened 2 months ago? Our recollections of it are different. Our understanding may have varied as we go along. In our country, we call them fishing stories. Every time you tell the story about how big the fish was, it gets bigger and bigger and bigger. Well, the same thing happens with firefighters. Every time you tell the story about that fire, the fire gets bigger and bigger and bigger each time. So if you're comparing today's fire to one that was 5 years ago, you're going to have this memory of this massive fire that could have been just the size of this flower here. So there's always that challenge. However, how can we take and add some knowledge to it to pair it together? And that's where research comes in. The lower level where we're going to there is using the experience gained by the firefighter to answer questions. So I'll talk about it a little bit in the presentation, but experience is very much based on perspective, what you saw and what you did. There is no point where you can see the whole incident. You don't have the opportunity to know what it looked like from the outside and the inside at the exact same time. Because of that, your experience has a perspective associated with it. If we could take that perspective and experience, research it a little bit so we understand it a little better, and then apply it back into our tactics and strategies, maybe we can kind of come up with the best of both worlds as we go along. So we're not saying put researchers on the fire ground. As a researcher, I have 2 brains. I have one that operates on fireground and one that operates when I do research. If I were to analyze every fire like I do when I'm working, when I showed up, we'd probably accomplish nothing. But if I was to perform research like I do firefighting, we'd just put the fire out every time. We wouldn't learn anything. So it's the best of both worlds, and how do we put it together? So we've been doing research for the fire service for about, with the fire service for about 10 years at UL. And I set out to come up with a presentation where I could review the last 10 years of research for you and kind of give you an overview. And as I started doing that, I realized there is absolutely no way I could cover all 10 years of research in 45 minutes. And Renee is very specific that I stick to the schedule. So we're going to actually go over the top 10 things we've learned in the last 10 years of research. Much easier to accomplish in 45 minutes. So the first thing that came out of all of our research is that science, although very boring, is important to understanding how a fire behaves, or fire dynamics. If we don't look at the science, we can't understand how the fire behaves. This is important as I look at it. When I read fire training manuals, they talk a lot about fire behavior, assuming the fire has a wish or a goal. And sometimes that goal changes depending on where the fire is located or how the fire feels that day, which really doesn't work that way, obviously. There's a set of physics and chemistry it has to abide to, and it will do that at every time. So if we understand those physics principles, we can understand fire a little better. Give you an example of that. In 1917, there was a scientific paper on what's called Thornton's rule, which stated that the amount of heat that comes off a fire is directly proportional to the amount of oxygen that's consumed. We have used this for the last 60 or so years in what's called oxygen consumption calorimetry as engineers, where we can determine the amount of energy that came off the fire by measuring how much oxygen is left in the smoke. If we know the quantity of the smoke and we know how much oxygen's in it, we can determine how much was consumed and thus how much energy is given off. In the fire service, we often forget about this because we're so focused on the fire. So I want to take this to the fire tetrahedron, which is in the upper left there, and let's break it down a little bit. The fire tetrahedron has fuel. Here's an example of some fuel. It just happens to be the chemical formula for methane. And it has oxygen. If you want to completely burn 1 molecule of methane, you need to use 2 molecules of oxygen. That's called the balanced chemical equation. If we add heat to it, what are we going to get? We're going to get some sort of fire. In addition to that, we're going to get some products after the fire. We'll get some CO2 if it's completely burned, and some water vapor. This is very important because the amount of fire, or energy, that came off is now proportional to the oxygen that was available. So, as we talk about the products, we can simplify things a little bit, because I like to kind of break it down to the important pieces. So instead of having methane, we're going to have some pellets. If we take our pellets, we add some heat to it. If we add enough heat, do we think we'll get a fire? Most likely, right? If we add enough heat to it, we'll get a fire. That fire will release some amount of energy. Rather than calculating the exact amount, we're going to say it's 2 units of energy for each pellet that we burn. So we get 2 units of energy and some smoke, and most likely some fuel left over as well. If we take 2 pellets, we add heat to them, we still get a fire. We actually get a larger fire, and we get 4 units of energy. This is great knowledge for the fire service, because this is as far as typically we would go. There's your science. What was missing was when we put the pellets inside a box, we limited something. We limited the amount of oxygen available. So if we take the same pellet in a box, we add heat to it, instead of getting 2 units of energy, we're probably only going to get 1 unit of energy off, because there's just not enough energy there, oxygen there, to create the energy. If we double the amount of fuel, in our country we call this hoarding conditions or over-furnished conditions, a lot more fuel. The thought was we would get twice as much energy. Burns a lot hotter, that's a challenge for firefighters. In reality, we can only still get the same amount of fire, because we only have the same amount of oxygen. When we add an opening to it, we can actually increase the size of the fire, or get back to what it was when it was burned in the open, to our 2 units of energy. Seems very, very simplistic, but when we look at fire tactics, this exact concept sometimes gets lost. The tactic of ventilation in the fire service is to make an opening. When you make an opening, you let smoke out. Conservation of mass says that that smoke just doesn't disappear, that something has to replace it in the structure. Conveniently, it's usually air. When air is added, it increases the size of the fire. That tactic specifically in ventilation sometimes was lost. Understanding the science of where it comes from can really help us understand how to apply the tactic effectively. So of course you'll say, well, we don't go to pallets and boxes often unless we're training. So let's take a look at this using some real furniture. I've got a furnished compartment here. It has a chair, a sofa, 2 end tables, a coffee table, a TV stand, carpeting and padding, and curtains. If I add it all up, theoretically, I should get about 10 megawatts of energy out of that fire. So we let that fire burn, and you'll notice it burns very quickly. Modern fuels are really great at this. And in about 2 minutes and 45 seconds, we reach what we call flashover, flames throughout the compartment. We hit our peak heat release rate, and we've maxed that out. We're going to compare that to when we over-furnish the compartment. So if we take 6 chairs and 3 sofas, now we're somewhere in the neighborhood of 27 megawatts of energy. We're going to put it in the compartment. We're going to burn it. We light it in the back. It takes a little while for it to get going here. We talk about the fire dynamics of this. It's about the orientation of the fuels. In the earlier compartment, we had a curtain. The curtain allowed the fire to grow rapidly up the curtain and spread across the ceiling, which caused it to spread to the sofas faster. In this instance, we don't have any curtains, so it takes a little bit longer to spread. So at 2 minutes and 45 seconds, we're not quite to flashover yet, but as we watch things progress, we progress the same way. We develop a hot gas layer. That hot gas layer starts to radiate energy back down to the fuel that's in the compartment. We'll see eventually the covers melt off some of the chairs and the sofas. As that happens, those ignite, floor to ceiling. About 4 minutes and 45 seconds or so, we've reached the flashover in the compartment, and we'll reach our peak heat release rate. So which one released more energy? It's a trick question, right? They release the same amount of energy. But in the fire service, we focus on fuel. We focus on saying that the more fuel in there, the hotter the fire burns. Somewhat accurate. My friend Stefan Svensson would say, well, it depends. And he's right. It depends on a lot of things. In this instance, we burned 2 different compartments, and we got about the same heat release rate. Conveniently, we had to use the compartment twice because we were trying to save a little bit of money. And the second time we burned it, the ceiling fell down. When it did, the energy release went up because we added more oxygen. And then it fell down again, and it went up further. It's subscribing to Thornton's rule of the energy release being proportional to the available oxygen. When I learned the fire triangle or fire tetrahedron, when I joined the fire service in 2001, I learned it as in a parking lot. I didn't learn it inside of a compartment. So if we can take that one step forward knowledge leap, I think we can have a lot better understanding of how fire works. Number 9, my favorite one, no amount of technology is going to make it, to replace the need for you to know what your job is. We can give you the fanciest fire apparatus. We can give you the best gear that's out there. We can give you $10,000 cameras. We can give you cold cutters or cobras or it doesn't really matter, right? We can give you all the tools that you could possibly have. If you don't know how to use them, it's not going to make you any better of a firefighter. In many instances, it's actually going to kind of take away from the important tactics. When we look at turnout gear, we can trace in the US the point in time where we stopped learning about fire dynamics and started learning about how to wear your turnout gear correctly. We replaced knowledge about how the fire works with knowledge about how gear works, and in that instance, we lost some knowledge. When we started wearing breathing apparatus, we now could go further into the compartment, but we had to learn how to put something new on. When we did that, we focused on drilling on that and not necessarily on how to take the line off the apparatus. We can take this to apparatus, we can take this to cameras, we can take this to fans, we can take this to nozzles. Everywhere I go, I'm asked, you do a lot of research. I have 2 hours, what should I train my firefighters on? My answer is, get water out the end of the hose and as fast as you possibly can. And a lot of times, you think that happens a lot faster than it really does. Under a minute would be good. That's pretty hard. That's a challenge, but that's knowing your profession and knowing the tools that you have. Thermal imagers can help you indicate that there's a fire in a void space, but it can't see through objects. This is a thermal imaging view of a floor. Happens to be a firefighter crawling above the floor. The floor has carpeting on it. When he pokes a hole in the floor, we see, look at that. There's a fire underneath the floor. The camera can't see through the floor because it's insulated based on the carpet. We ran a couple of tests to look at this, more on structural collapse, but the data fits very well. Where you can have a compartment, those temperatures are in Fahrenheit. You can have a compartment that's 600 or so degrees Celsius, and the floor above it is 20 degrees Celsius. The camera's looking at the 20-degree floor, and it's just taking time for the energy to go through. Understanding how that camera works is really going to aid in your understanding of where to use it and where not to use it. One thing that we love to say is that they can tell us what the temperature is. This gave us an understanding of how we operate on the fire. Let's take a look at a thermal imaging camera view in the upper left there. And we see that we've got a compartment at the end of a hallway. It happens to be this fire right here, fire at the end of the hallway. The fire's growing in the compartment. We can see the gas velocity is increasing, and we can see the temperature on that readout is also increasing. However, when I compare that temperature, the black line, to the temperatures I had throughout the hallway or at the end of the hallway at different elevations, we see in the beginning, temperature looked pretty good. You know, it's relatively close, probably within 20% or so of what the actual temperature is. But at some point in time, the smoke got so thick and so dense that the camera was now reading the temperature of the smoke closer to me and not the smoke at the end of the hallway. So I felt the temperature of the smoke was 200 degrees Fahrenheit, when in reality, the temperature of the smoke was approaching 600 degrees Fahrenheit. It gives me a very poor understanding of where I should be going and where I shouldn't be going if I'm relying on that temperature readout. In the US, the standard says the temperature readout has to be on the camera, so every camera you get will have one. If we can understand how to use it, we certainly can become better operational firefighters. So I do have to contradict myself slightly because I say we focused a lot on turnout gear and we focused on how to use it. Well, I think one of the things we forgot was what it actually does for us. We taught firefighters how to put it on. We taught them how to wear it appropriately. We even timed them how quickly they could get it on. We've engineered it so it works the best it possibly could, but no one ever tells them exactly how it works. Knowing how it works is critical to knowing where you can be and where you can't be. Physics says energy always flows from high to low. My mother used to say you'd let the cold out of the refrigerator. She was lying, you would let the heat in. However, still physics. When we look at how turnout gear works, it's a bunch of materials or separate layers designed together to delay the energy transfer coming in to the skin at the end. So if the red bars represent an energy flux to the outside of the gear, we notice that given enough time, that energy transfer can make it to the skin. There are some convective losses associated with it. There is some, it's not 100% effective. You do lose some of it as you go through. The air gaps provide a very good delay in transfer. It's much like we use when we put insulation on the outside of buildings. We use insulation with air gap and another insulation to delay the energy transfer from the hot building when we're trying to keep it warm in the wintertime out, or in the summertime, the hot air in. We take a look at two firefighters here in the bottom right. They're going in and they're putting some pallets on a fire. We see our one firefighter that stays out of the room, relatively cool on our thermal imaging camera. However, the one that keeps going into the room, every time he goes in, he receives more and more energy. His gear becomes saturated with energy. If this were me and I was the guy outside the room and this guy came out of the room and said, man, it's hot in there. I gotta go take a breather outside. I'd be like, you wuss. It's not that hot. Why? My perspective was, I was outside the compartment. I didn't get the energy. He got the energy transferred to him. If we were both caught in an extreme fire event at the same time, which one of us is going to get burned faster? The one who had more energy in his gear to begin with. Well, how's it supposed to work? You go into a fire, you start receiving energy, you may have some convective losses if you're in the good part of the flow path, and at some point after you go in, hopefully, you or someone else puts water on the fire. When they do so, the fire stops producing energy, you stop receiving re-energy to your turnout gear. What does this result in? Well, in this particular instance, the individual wearing that gear may have felt nothing. Quick story behind that. When I joined the fire service, I'm a brand new firefighter. I was a little cocky, I can admit that. And I had an instructor that said, you know what, kid? I'm going to teach you what it means to be a fireman. I'm going to make the hottest fire that I possibly can in this training facility, and you're going to have to go in and put it out. So me and my best friend at the time, who joined the fire service when we were 16 and 17 years old, because they had flashing lights and sirens, not because we really wanted to be firemen. I can admit it. I still do it because of that. We're getting ready to go in. We're pretty scared at this point because, you know, we're intimidated. This guy's got a massive mustache, so he must know what he's talking about. So he lights the fire. He comes out, and his gear is actually smoking. And I'm like, you want me to go in there? That's your intent? So we take the line in, and we're rushing as fast as we can because they tell us you got to be fast. And we get in there, and we put water on the fire, and fire goes out, and we come out. And the instructor goes, so was it hot in there, kid? Did you feel it? And I was kind of like, yeah, that was bad. And then I turned to my friend, I go, did you feel anything? He goes, no, did you? No. What did we do wrong? We didn't do anything wrong. Our gear worked exactly as it intended. The instructor's gear worked exactly as it intended. He was just in there longer, so he received more energy than we did. If I had been taught this about my fire gear when I first joined, I probably would have been slightly more reckless, but I would have done it with knowledge of knowing where I can be and where I can't be. Firefighters are taught 3 modes of heat transfer: conduction, convection, and radiation. You memorize them. They're test questions. How do they relate to you as a firefighter? How does that energy come to you? If you're receiving energy by all three modes, that's probably the worst. How do you reduce the amount of energy that you receive when you're in an environment? Get yourself out of the flow path so you're not getting the convective flow. Get away from the fire so you're not getting the radiation. Loosen your turnout gear up a little bit so it's not conducting to your skin as much. If we learn these things, we can operate in very different environments where we didn't think we could be to begin with. Strange part is we knew a lot of this. 1972 at the Fire Department Instructors Conference, a gentleman named Zevotek, who has become very famous in my office now, we actually call this a Zevotek chart, decided that there were three regions really for firefighter operational limits inside a building. There was the routine region where you could go, you could be there for a long period of time, probably nothing was going to happen to you. There was the ordinary region where you could go, you could be there for some period of time, most likely tens of minutes, probably more than air than you had in your breathing apparatus, and you'd be fine. Then there was the emergency spot, where you could probably be there for less than a minute, because that's what your gear was really designed to protect you against, was that flash fire event, that rapid fire growth. If you got out in under a minute, you're probably okay. If you stayed there longer than a minute, you'd probably get burned. One of the gentlemen in my office, Jack Regan, who sometimes is like, sometimes I worry about him, and then other times he's a genius. This happens to be one of his genius moments. He went back and looked at recent research on skin burns and where firefighter face pieces start failing and where firefighter turnout gear starts failing, and he overlaid them on the graph. A would be the temperature at which skin is destroyed. Conveniently, above that temperature, we say that's where firefighters' ordinary operating range is. D would be the typical exposure to a firefighter. When we get above that, we say we're in the ordinary operating range. E and F and C and B happen to be where face piece failure has been found. Very close to that emergency range of operations. It's not far off. Understanding which region you're in is pretty key to understanding how long you can be in that region. Now, I would take it one step further. I'd say there's definitely some spots on that graph where you'd have a high temperature and low heat flux, or you'd have a low heat flux and a high heat flux and a low temperature. Those are both possible, so they're probably just as dangerous. But for the most part, this guy had known what he was talking about, and it was probably almost 50 years ago now. Getting behind a closed door is an effective method of isolation. This works for occupants, and this works for firefighters. I think the piece of this working for firefighters is sometimes lost. If you get disoriented in a building, I was always told to sound my alerting device, make a lot of noise, call a mayday on the radio. Nobody told me to get behind a closed door. The difference in being behind a closed door and out in the open are drastic. So we look here at this video. We may need to, nope, the video's playing, we're good. So we start to see our temperatures on the right. The upper picture is the living room, so you're out near open to the fire. So there's a fire in a bedroom, it's open to the living room area. This is a bedroom right next to the room that's on fire. 2 minutes into our fire, we're not seeing a whole lot happening. We're starting to see some smoke on our camera in the upper left there. Starting to see our temperature rise in our living room at that location. Closed bedroom's got some smoke coming in it, but nothing's going on. So we've been inside a house that's on fire for almost 4 minutes now. Our closed bedroom, it's really not that bad. I mean, there's some smoke coming in, but really, temperature isn't going up. We look at the living room temperatures. Ceiling is exceeding 300 degrees Fahrenheit, going up to 400 degrees Fahrenheit. The 1 foot temperature is fairly low, but the 3 foot where I'd be kneeling, that's starting to exceed skin burn temperatures fairly quickly. Where our closed bedroom, really not seeing a whole lot going on. Firefighters show up somewhere between 6.5, or 7 minutes, depending on where you are in our country, depending on how close to the fire station. Depending on what tactic they choose, they may be able to rapidly extinguish the fire. It may take a little more time. In this instance, it's about 7 minutes. They put water on the fire. We see temperatures start to reduce inside the living space there as they're cooling the fire. They reduce fairly rapidly once they put water on the fire, but the damage is pretty much already done. When we look in our bedroom, still very, very low temperatures. That goes for both occupants and for firefighters. If you got in a place where you'd be in trouble, behind that closed door, even though it's a hollow core wooden door right next to the fire room, still stayed fairly low. It actually stays below the threshold of any sort of damage to the skin for the entire experiment. Pretty important piece. Somehow we missed that in fire training. We also missed that when we talk about fire safety education. Did some time as a firefighter in College Park, Maryland, which is right next to the university. We're responsible for going to the university and conducting fire drills. The lowest ranking guy had to do a little public service announcement after they came out of the fire alarm, where we told them that they needed to dial 911 because their fire alarm wasn't connected to call anybody, and that they needed to close their doors when they left their dorm room. Do the same thing for kids. When we go to their classroom, we teach them about stop, drop, and roll. We teach them the importance of having an escape route. We teach them the importance of having an emergency plan in their house. We teach them the importance of not using matches. We miss the part of make sure your door's closed. If your door's closed, you can have a big effect on the fire. Experience is very much about perspective. And as you learn this, it's not just in firefighting, it's in pretty much in our entire life. Our experience is 100% based on the perspective we had when we experienced it. Here's an example of a fire. If I'm a firefighter sitting at the bottom of the stairs and this happened, most likely I'd need to change my underwear. It's a little exciting. I'd come out, I'd probably be all amped up, I'd probably be upset. If this is my perspective and I came out and somebody said, hey, did you guys see when so-and-so put the water in the window? I'd be like, yeah, I saw when they put the water in the window. Did you see what happened on the inside? But my perspective is very different. If they had said, did you see when so-and-so put the water in the window using a fog stream and covered the whole window up and blew air in there? I'd be like, they're an idiot. I wouldn't be mad at them. I would say, we got to educate them on a better way to put the water in the window. But if my perspective was the earlier one, I would say we never should put water in a window that has fire coming out of it. It's important to remember that your experience is all based on your perspective. So taking a step back sometimes and looking at others' perspectives can really help understand the experience that you gained. You need to cool as you advance. And I almost titled this gas cooling because it's interesting. Much like in our country, when we talk about fire streams, and we actually mean the water that comes out of the nozzle, not a stream of fire somewhere. It'd be more interesting if we could produce streams of fire, but that's not what happens. We produce streams of water, but we call them fire streams. When we say gas cooling, we really mean you need to cool as you go into the fire. If you don't cool, you could be in trouble. One of the things that we talk about is we talk about energy transfer. As a kid, we knew that the sun produces energy. If we focus said energy, we can start a fire. I even have in a survival kit when I go camping, a magnifying glass for this particular incident. Now I realize it's usually hard to start a fire when it's raining, and the sun's not usually out when it's raining, so this is probably not going to work for me, but I still have it with me in case. But what are we doing? We're focusing the energy of the sun, which really could create a burn. If you're like me and you go to the beach, you get a burn in about an hour and a half. I'm just very fair-skinned. My wife, on the other hand, could stay there all day with no sunburn. It's not quite fair. But however, if we focused that energy that took time to give me a burn and we did it and focused on a specific point, we could produce that burn much faster. It's all about how much energy and how it's focused on the transfer. So let's take this to the firefighting perspective. In this example, we're going to go in this door. Ignore the fact that you could put water in the window. I would probably put water in the window first. But you're going to go in this door and you're going to go down the hallway to put the fire out. A lot of people talk about the things you see when you're approaching a fire. So you're approaching the fire and you're crawling down the hallway and see this. My introductory fire training would tell me, I don't need to put water on that. It's not a hazard to me. My feeling when I look at my temperature there, everything below the 3-foot level is very cool. But then something happens. And the amount of energy transferred to me rapidly increases. The heat flux increases. If I had put water on that before this event, do we think we'd ever have reached that event? Probably not. You need to cool as you advance towards the fire. Risk profiling. This is big. A lot of the time when we talk about risk profiling, we talk about the thought that if you see fire coming out a window, there's no space that's survivable inside that house. That was what I was taught. When I started to try and balance that against what we see in experiments, we could see fire coming out of 2 windows. The entire left side of this house is on fire. Both of these rooms have flashed over. They're in excess of 600 degrees C, floor to ceiling. Very not survivable. We look at this victim that's right outside the compartment. And when it comes to gas concentration, he's doing pretty good, actually, at about the time when the fire department arrives. When we look at temperature, though, he's off the charts. It's probably not a survivable space. We look further out into the house, further away from the fire, and we see that the further from the fire we get, the less energy they're receiving. That makes sense. But the thought was that gases are what's killing these victims. That down low, you're getting all this smoke and it's exceeding these toxic levels and it's killing these victims. When we look at the effective dose of gases that they're receiving, when I say effective dose, I mean carbon dioxide, carbon monoxide, and oxygen. Combined together, we can calculate a fractional effective dose, or the amount of dose it takes for them to reach a fatal point for 50% of the population. When we do that, the only victim that exceeds our fractional effective dose criteria of 3, which is the fatality level there, we see is the victim that was up on the bed, laying on top of the bed. The victim behind the closed door, number 2, no problems. The victim 4, way down the hallway, no problems. We couldn't measure gas concentrations at victim 5, but I can extrapolate, since they were on the floor way out there, that they're probably not having a problem. This makes sense when I actually try and think about it, because a fire can't burn without oxygen. That level at which that happens is somewhere around 14% oxygen. I know some fire protection engineers that use oxygen depletion as a method to prevent fires. They pump nitrogen into a space to lower the oxygen. Does anybody know what they lower the oxygen level to? 14 to 15%. Can workers still go in there and perform maintenance on the computers or the electronics or everything? Yeah. Can they be in there for 8 hours? No. They'll get a massive headache. But 2 hours, they'll probably be all right. So, well, hopefully you're not staying inside the house that's on fire for 2 hours. If it's taking the firefighters 2 hours to get you out, that could be a problem. But if that's the case for where the fire can't burn anymore, that's also the case for a lot of the products that go with the combustion of the fire can't get there. So down low at the 1 foot level, laying on the floor, fairly survivable spaces for a good time throughout the fire. So if we're going to use the amount of visible flame on the outside of a structure as our method of profiling the risk within inside that structure, we probably don't have the data we need to really answer that question effectively. Now in the fire service, my friend Stefan Svensson pointed out again yesterday, in the US we focus a lot on victims because they're always occupied. It's assumed the house is occupied unless it's not. Data probably tells us most of them are unoccupied, but once every 3 weeks there's a house that was not occupied or supposed to be not occupied. Fire service shows up to a fire and they pull someone out who was not supposed to be in there. Person survives, and thus the fire service should search every house that they ever go to. Probably not the best method, but it does illustrate the challenge that we have that you don't really know whether it's occupied or not. So we do probably need to make some assessments on that. If we're going to make those assessments, we probably should do it on data rather than our perceived understanding of what the rest of that house looks like. The last tactic is really oversimplifying things. I was going to put a video in here of a gentleman that they call the fire SUV. It's a comedian in the US. Talks about the very difficult things that the fire SUV does on the scene, or in our country, it's the fire chief that arrives first. Spends a lot of time talking about how that individual just says, well, if you could take water and put water where there's fire until there's no more fire, then we've done our job. It's pretty simplified, but it's really not that inaccurate. Water makes things go better. The amount of water you need is kind of a debate, whether you're in the Netherlands or you're in Sweden or you're in UK or China or the US. We used US nozzles, so they're flowing a lot of water in excess of 300 liters a minute. So we used them on 25 different fires that we put out. Some of them we sprayed it from the outside, some of them we sprayed it from the inside. If we sprayed it from the inside, we cooled while we advanced down the hallway. In none of the incidents did we exceed the 950 liters to extinguish the fire? Why? Well, as researchers, we knew exactly where we needed to put the water. So we put it there, and the fire went out. If you know exactly where the water needs to go, you don't need a whole lot. Things to keep in mind, though, as you look through this, you need water to fill the hose. We didn't measure how much water it takes to fill the hose. Our hoses are really large, so it probably took more water to fill the hose than it did to put the fire out. It's reality. What can I say? You need water to clean up after the fire. It's not necessarily, I mean, this was measuring till the fire was what we called knockdown, so no more visible flame, no more audible combustion. But afterwards, you're going to need to move things around. You're going to have to put the rest of the water on it. And also, why would we just take the minimum with us? That doesn't seem like a great idea either. We should probably have some sort of safety factor in it. As we have engineers that designs bridges, if they design bridges just to support the exact number of cars that would be on that bridge, none of us would drive across that bridge. Fire service probably should take a hint there and bring a little more water with them than they need, or hook up to a hydrant to get more water if they need it. The key is, though, is not to let that action delay other actions. Should you just use what water you have with you to see what impact it has before you take minutes to hook up to an additional water supply? That's a huge debate in our country. Should you use what's there? Most of our engines are bringing with them somewhere in the neighborhood of 1,500 liters. We have a lot of water on them, and that's the smallest ones. The larger ones are 6,000 liters. Based on what we recorded, you put out a lot of fire with that amount of water, as long as you know where to put it. It's interesting, my colleague and I were looking at the picture here, and there's a joke going on in our country about how you need to, that's a big fire, so you need big water. So you need to pull a bigger hose line. And we joke that we'll let you pull the bigger hose line, we'll pull the smaller hose line, but we'll take it where it needs to go. We'll put water where it needs to go, and it'll be more effective. Not trying to pick on anybody, but is that stream really doing a whole lot to that fire? It looks really cool. I wish I was the firefighter in the picture, by the way. I also want to know why there's a chainsaw on the ground, because I heard you guys don't cut roofs open like we do. But all joking aside, if we know where the water needs to go and we can get the water there, that's probably the best option. Just assuming that the fire's larger needs more water does not add to the conversation. A lot of the time, you apply water to a spot and then you need to move the line someplace else. If the line's too big to move by one or two people, it can't get to the other spot and the fire grows back by the time you get there. It's all about knowing where it needs to go and being able to get it there. In the measurement, we had 2 rooms of fire, we had 1 room of fire, we burned through the top of our structure a few times. There's a good amount of fire there. We didn't have a problem there, but we still were able to put it out with the water that was available. So that was a quick look at 10 years of fire service research, picking out 10 things that I would pick to try and educate every firefighter if I had the option to teach to every firefighter. There's a lot more out there. If you're interested, feel free to head to our website. We have free online training courses you can go to. If you're interested more in learning about how those strange Americans do fire attack, my colleague Keith is going to give a presentation this afternoon. It'll be in English both times, I apologize. But on a project we did on fire attack, looking at that specific information, we'll go into a little bit more information about the victim survivability piece. If you're interested in that, please feel we can plug our conversation. If you want more information, please get a hold of me. That's the number to my desk. That's my email. It takes me a little while to answer them, but I do answer as many of them as I can. If you happen to lose that information, you still have a question, our general email address works just fine. Little secret, it goes to my desk, so if you lose my information, just email our general email address. So I only answer that like once a month or so. But with that, questions. Does anybody have any questions on what we're doing for research or what we have going forward?
That's where I come in. With,
all right.
Yeah.
It's good. I'm not going to throw that. I'd hit somebody and it would not work out for me.
Thank you for your impressive presentation and sharing the knowledge with us. Questions? Yeah, that's...
Thank you very much. Dietmar Kuhn, National Fire Academy of Luxembourg. I have one question. Considering all the research you did in the last years, how can you explain yourself why you still do things like roof ventilation and put firefighters on big danger, even losing them?
We have 1.1 million firefighters in the U.S. A simplistic answer, but if we take it more seriously, the room here has approximately 100 to 200 people in it. As an engineering researcher, if I went around our country every day and I presented the information we have, I could hit a very small fraction of that, probably about 10,000 in my career if I really tried hard. We use free online trainings. We see somewhere in the neighborhood of 100,000 to 200,000 users on our free online training. Conveniently, about 50 or so thousand of those are from out of our country. So we're still hitting just a very small fraction of it. We're working very hard to get our research in fire training manuals, but much like codes and standards, they're consensus-based. So what you believe goes in the standard just like what I believe does, and it doesn't necessarily need to be referenced in science. So my argument is, have a reference for it. Like I said in the beginning, I can't put anything in a paper that doesn't have a reference for it or that I didn't research myself. I kind of feel we need to do fire prevention, fire safety, fire operations very similarly. Don't forget what we already know. That's one reason you go back and reference things. But also make sure that the next guy that has a question that can't ask me directly has something to read to be able to go back to it. So yes, we do put people in bad spots. I agree it's a challenge. Go to YouTube. You can see as many of them as you would like. However, it's a scale problem for us, and we're trying to attack it as many angles as we can.
Normally, everything in the United States is bigger. We have in Europe 3.2 million firefighters, so the problem is even bigger in Europe, I think. But okay with the question? Yeah. Other questions? Oh, that's that's a long way. Hi. Oh.
Got it. Well, you said something about technology, that there's no amount of technology that can replace you if you don't know your profession. And in some safety regions in Holland, there's a lot of money is being put in technology, whereas training is, well, training can be better sometimes. So do you think there should maybe be a shift to like put more money in training than to put in technology?
It's a tough question because training costs money, and I agree with that. But as I look at my experience in the fire service and the amount of time that I am spent training versus the amount of time that I'm spent doing other things, it's really not proportional. I don't like to advocate to buy the newest tools because there's a lot of fire departments that don't have the money to do that, and their choice is between, you know, making something work that they already have and buying something brand new. So I don't like advocating spending more money on different things, but I do advocate on spending more time on training. If you have an opportunity to visit a fire station, and I apologize to the firefighters in the room because you are very busy individuals, you do a lot of fire prevention, you do a lot of equipment maintenance, and you do a lot of other things. But if it were my house that you were protecting, I would like it if you put your gear on once a day and practiced it once a day. I'd like that you pulled the line off the apparatus once a day. Why? Because you work every 3 days in our country, and there's time to lose that practice over those 3 days. I don't think it's a huge ask. I think if we spent more time doing those very simple things, we could really increase our effectiveness drastically. Quick story on that, LA County Fire Department in our country went through and revised their training tactics. They started to do an exterior fire attack, something they'd never done. They saw reductions in loss of damage and property. And the first question I asked was, well, how did you implement the new tactics? And they said, well, we brought everybody to the academy for a full 8-hour day of training and followed that up 2 weeks later with another full 8-hour day of training. Was it the new tactic that they were using that reduced the injuries and the death? Or was it the fact that they spent in 2 weeks 16 full hours on training on how to get the hose off the apparatus because that's part of the tactic that they were working on? It's a really interesting question. I don't have the answer. I'd love to have a degree in psychology because I think I could answer more fire service questions with that.
So would you say your skill level is important?
Very important. Firefighters are very much so, including myself, hands-on learners.
Yeah.
work to their strengths.
Thank you. Last question. You know, if you say something like last question, then... Okay. Robin, thank you for your presentation.
Thank you.
You know, when you were speaking, I was thinking, you say we have a lot of devices, a lot of systems, but you have to think normally. We call it boerenverstand. And I tried, how do I translate boerenverstand into English? We call it use farmer's sense. Farmer's mind, I don't know if you understand it, but completely. Common sense, yeah. Yeah, but boer.